be looking at implicit differentiation, that is implicit what function. And we can see a question before us: x squared plus y squared minus 2x minus 6y plus y equals 0. Find the y dx and the square y over the x squared at x equals to 3 and y equals to 2. So at x equals to 3 and y equals to 2 is the condition given. Okay, so quickly let's dive into this step-by-step solution. Write our solution first, and I'm going to show you something quickly before we continue. I want you to know that there's a difference between this and this, because if you look at this function, this equation given before us, you can come across equation like this in partial differentiation or implicit function like this. They will not tell you whether you have to use partial differentiation or implicit method. They will not tell you, but you should be able to identify it, and that is what I want to show you now. Please, this is very, very important. Try to identify the symbol. This symbol here represents partial differentiation. Look at the way this one looks like. Look at it, the way it looks like. Is it not different from this? Look at this one. This one look like entirely D. You will see that this, the way it is being written, you can see it here, is different from this. So here now, the way it is being written is D, the normal way of writing D. Why this one is not like that? So this at the left here represent partial differentiation, while this one at the right here represents total derivative, or you can also use it for implicit function like this. Now, if you see this question now, let's assume we are to differentiate partially. They will just put this one here. If it is partial differentiation they want, they will just put this one here instead of this. Are we following? So if I'm to use partial differentiation method or partial differentiation, if I'm to differentiate this one partially now, let's take notes. The way I will differentiate this partially is different from the way I will differentiate it using implicit method. If it is partial derivative, for example, now look at this one. Partially, I'm differentiating y with respect to what? With respect to x. So what I will do is that since it is partial, from the word partial means I will not consider all. I will consider some parts, leave some parts. So I will only consider y with respect to x only. Any way that does not have x will change to 0. You can watch my video on partial differentiation for better understanding. I will only focus on where there is x, and anywhere that does not have x will change to 0. Like this 6y, it will change to 0, and like this one too, it will change to 0. That is to tell you that it is partial differentiation. And if it is partial differentiation, this is what you likely come across. But if it is implicit, you will not see something like this. You can see both the function of x and y here, but you will not see this. You will not see this. You will see this. So this tells you that you have to use implicit method. And what is implicit method? In implicit method, we still use the same method, the same way of differentiating it, but there will be little bit difference. You know, if I'm to differentiate it, for example, now the y dx. If I'm differentiating the y dx, now I'm differentiating with respect to x. So I will differentiate this one, the normal way of differentiating it. That is the normal method of general method. I will use it here. I will differentiate it. Okay. So I will differentiate this one using the normal approach. Okay. But what about this? So it will now look as if I'm differentiating y with respect to not longer x, but with respect to what? Y, because y it is there. So if it is partial differentiation, this will change to 0, but in implicit differentiation, it will not change to 0. I will still differentiate it using the normal approach, the normal method. You understand? That is, the power will multiply it, then subtract 1 from the power using the normal approach. But I will then do something. Whenever I'm differentiating y with respect to y, I must add the y dx at the back. Immediately, I must add the y dx. Like this one, if I differentiate it with respect to x, I don't need to add any dy dx because it is a function of y with respect to x. But if I'm differentiating a function of y with respect to y himself, I must add dy dx at the back. I hope that is clear. Okay, so if I'm differentiating y with respect to y, function of y with respect to y himself, you must add dy dx. But if I'm differentiating y with respect to x, you don't need to add dy dx. So that is the difference between implicit function and partial differentiation. So this work, I just wish to show you that for you to know that it's a difference. Now we're given a problem. This is what we're given, and this is what we're asked to differentiate. In implicit differentiation, let me tell you the key thing in implicit differentiation. Whenever you are differentiating with if you look at this function, you will see x, you will see y, right? Now, and we are differentiating y. We are differentiating y with respect to what? X. How come does y still occur in this equation? How come does y occur in this equation? Now, whenever you are differentiating y with respect to x, you use normal method of differentiation. Okay? But whenever you are differentiating, we are differentiating y. If I'm differentiating it with respect to this y that is already here, then something we have to adjust something. We have to adjust it. Okay? So take note of these things. Whenever you are differentiating with respect to x, you use the normal way of differentiating. But if you are differentiating with respect to y, immediately after you differentiate it, you must add dy dx at the back. This is compulsory. Very, very, very compulsory. Immediately, if you differentiate with respect to x, you differentiate it the normal way we differentiate using the normal approach. But whenever you are differentiating y with respect to y, whenever you are differentiating with respect to y here, you must add the y dx at the back. Immediately after you differentiate it, immediately add the y dx to it. Whenever you are differentiating with respect to x, you don't need to add the y dx. Whenever you are differentiating with respect to y, you must add the y dx. So please, let's take note of that. Okay, so let's continue. So if I differentiate this using general method of differentiation, normal approach, you see, you can watch my video on that. You can check my comments. You use this 2 to multiply it, right? And then you subtract 1 from the 2. That's just the simple way of differentiating using general method. So you use the power to multiply, then subtract 1 from the power. So if I use 2 to multiply it, give me 2x, just as you can see here. And if I'm differentiating with respect to y, don't forget that I told you that whenever you are differentiating with y, immediately after differentiating it, you must add the y dx immediately. Now, if I'm differentiating with respect to y now, using general method of differentiation, I will use the 2, which is the power, to multiply it. It give me 2y. Then I will subtract 1 from the power. So when I use the 2, which is the power, to multiply it, it give me 2y, right? So if I subtract 1 from the power here, which is 2, it give me 1. That is y raised to the power of 1. And y raised to the power of 1 is the same thing as what? Y, which is this. But I told you that whenever you are differentiating with respect to y, you must always add the y dx. So that is one thing about implicit differentiation. That is one thing about implicit what? Differentiation. So that is one thing about implicit differentiation. You must always add the y dx. You must always add the y dx at the back. I mean, immediately after you differentiate with respect to y. Okay, so that is for that. That is for that aspect. Now we have already differentiated this part, this x squared. We have differentiated this y squared. What about 2x? If I differentiate 2x, it should give you what about this minus 2x? This minus 2x. If I differentiating minus 2x, normal way of differentiating, it will give us minus 2, right? Because of what? Because the power of this x here is 1. And if I use 1 to multiply 2, this minus 2, it will still give me minus 2. And you can see it here, right? So if I then subtract 1 from the power that is there before, it becomes 1 minus 1. And you know 1 minus 1 will give me what? 0. Right? So therefore, I will have x raised to the power of 0 here. And x raised to the power of 0 will give me 1. So 1 times minus 2 will give me what? Minus 2. So we still arrive at minus 2, which is 100% correct. So what about minus 6y? Minus 6y, the same approach, but don't forget that here is y, not x. Okay? So if I use the power to multiply this minus 6, it will still give me minus 6, just as you can see here, right? And if I subtract 1 from the power, it becomes, the original power we have here for this y is 1, right? So 1 minus 1 will give me 0. That will give me y raised to the power of 0. And y raised to the power of 0 is what? 1. Because any variable or any number raised to the power of 0 will give me 1. So that will give me 1. And 1 times minus 6 will give me minus 6. Okay? And then, but don't forget that I said whenever you are differentiating with respect to y, you must always add the y dx. Always add the y dx. This is what make implicit differentiation or implicit function differ from partial differentiation. Okay? So please take note of that. But what about if I'm differentiating a constant? If I'm differentiating a constant like 5 here, I'm talking about 5 here, this plus 5. If I'm differentiating a constant, you give me 0. So I don't need to do anything with that. If I'm differentiating this other side too, 0 will still give me 0. So this is what we have for that. Let's take note of that. This is what we have. Okay, but we need to collect the like term. We need to collect the like term. Why? Because if you see here, we have the y dx here. It's also present here. The y dx is also present here. It's present both. The y dx is present here. It's present here. So we need to collect the like term by bringing where there's the y dx in one side and those one that doesn't have the y dx in the other side. So collect the like term. So when you collect the like term, you will see that this plus 2y have the y dx, right? So you can see it here. And this, mind you that this minus 6 have the y dx because when we differentiated minus 6 here, we are differentiating with y. And so we added the y dx to it, as I've said earlier. So we have minus 6 the y dx, just as you can see here. You can see it here. Okay, so what will happen to this 2x? It will cross to the other side. This 2x will cross to the other side. Yeah. So when it crosses to the other side, what will happen to the sign? This 2x is the same thing as a plus 2x, right? So it becomes minus 2x, just as you can see here. Okay. What about this minus 2 that is here? Now let me show you something. You can say minus 2 minus 6 here. It's wrong because this minus 6 here is being attached with this dy dx. It's just like you saying minus 2 minus 6x. Minus 2 minus 6x. No, it is wrong. You can't subtract 6x from minus 2 because of that variable that is there. So this minus 6 here is being attached with that dy dx. So it's impossible for you to subtract minus 6 to the y dx from minus 2. So take note of that. So this minus 2, we have to cross to the other side, which will becomes what? Plus 2, just as you can see it here. Okay, so this is what we have if you collect the like term. Okay, all right. Yeah, so if you look at this again, you will see that I now want to bring out this dy dx that is there. Bring it out because it is common in both of them. So if I bring the y dx out here, I'll be left with what? 2y, right? So you can see it here. You can see 2y here. If I bring the y dx out here, I'll be left with what? Minus 6. So you can see it here, minus 6. Okay, right? So this side remains the same, minus 2x plus 2. You can see it here. Okay, so I want to make the y dx subject to the formula because what I'm actually calculating is the y dx. And to make the y dx subject to the formula, I will divide both sides by the coefficients of the y dx. What are the coefficients of the y dx? You can see I've already underlined the coefficient of the y dx. You can see it here, which is 2y minus 6. So that is, I will divide both sides by 2y minus 6. And if I do that, oh, wow, that is fantastic. We have something like this. Oh, we have something like this, right? That is perfect. But you can see that 2 is common in all of them. So I can factor out 2. You know, if I bring out 2 here, we have minus x, and 2 goes there, that will be what? 1, right? 2 into y, that will give me y, and 2 goes in 6, that will give me what? 3. So if I factor out 2, you can see it here. Then I can say these 2 cancel this what? These 2. So I'll be left with this. So this is my dy dx. But recall that we're given conditions. Recall that we're given condition that our x equals to 3 and our y equals to what? 2. So I will then substitute my x to be 3 here, and then substitute my y to be what? To be 2 here. So what will I have if I do that? That is wonderful. So we have something like this. We have minus 3 plus 1 over 2 minus 3. That will give me minus 2 over 1. Of course, you know, minus we cancel what? To cancel minus there. So I will be left with 2 over 1. And 2 over 1 will give me what? 2. So my our dy dx is equals to what? 2. What about the square y over the x squared? Now to differentiate the other one, which is the square y over the x squared, we are differentiating this dy dx for the second time. You know, that is second derivative. You know, this one now was when I differentiated it once, right? But this time now I want to differentiate this again to have my second derivative, which is the square y over the x squared, right? Square y over the x squared. So, and to do that, I will use an approach like what's it called? This quotient rule for differentiating. Quotient rule for differentiation. You can watch all my videos on those ones. I have videos on those ones already, and they are very, 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 very impactful. How will you know? Will you be able to know? Okay, if I'm to use quotient rule here or not? We use quotient rule whenever two terms divide each other. Like that is, if you have one term here, we use it whenever two terms divide each other, right? You can see here one term here. You can see one here, and you can see another one here. Fraction, right? One at the numerator, one at the denominator. So you use quotient rule for those kind of a differentiation. Okay, in quotient rule, you will keep this v constant, that is the denominator. You keep it constant first, then you will differentiate the numerator with respect to x. That will be what? V du dx. Keep v constant, multiply by du dx. That is for that. Then whatever you have minus. Now this time around, now you will then keep this one constant, the numerator, which is u constant. Then differentiate the denominator. That will give me u dv dx. Then everything all over v squared, that is the denominator square. That is v du dx minus u dv dx all over v squared. That is just it. Let's proceed. This is what I was trying to explain, that you will keep this v constant, you will not differentiate it. So you can see it here now that it's constant. Then you will differentiate this u with respect to x. You can see it now. Du, if I differentiate u with respect to x, that will be du dx. You can see it here now. You can see it. Minus, you know, at first you keep this one constant, right? You keep this one constant, right? But this time now you keep this u constant. You then differentiate this one with respect to x. So if I keep u constant, I will not differentiate it. You can see the u here now. Then I will differentiate this v with respect to it. That will give me the v dx. the v dx. So you can see it there. All right, now to get, I've gotten my u to be this. So how will I get my du dx? That is differentiating u with respect to x. I'm differentiating this u with respect to x. So if I differentiate this minus x, of course it will give me minus 1 because the power of this x is 1. So if I use 1 to multiply this, the invisible one here, it will still give me minus 1. And if I subtract 1 from the power, I'm still using general method, it will give me x raised to the power of 1 minus 1, and that will be x raised to the power of 0. And x raised to the power of 0 will give me 1. So that one, multiply the one we have here before, that will still give me 1. So you can see the 1 here. And this constant number, if you differentiate it, will change to 0. So we don't need to touch it. Let's just leave it. So what about, I've gotten the u dx. What about this one now? This is the v dx. Now this is the v dx. Now you notice that I'm differentiating v with respect to x, but do you see any x here? No. You remember that this is implicit function. So what will happen then? So I will differentiate it. It will not change to 0. So I will differentiate it with respect to y, then add the y dx at the back. Put it there. So if I differentiate this using the general method, the power of this y is 1. So if I use the 1 to multiply it, the invisible one here, it will still give me 1. Then that will be 1 times y raised to the power of what? 1 minus 1, because I will have to subtract 1 from the power. Y raised to the power of 1 minus 1. So y raised to the power of 1 minus 1 will give us y raised to the power of 0. And y raised to the power of 0 will give us 1. So that one, multiply that by the first one here. So that will give us 1. You can see the 1 there. But I told you that whenever you are differentiating with respect to y, you must always add the y dx immediately. So that is really the y dx here now. Okay, so if I multiply 1 with the y dx, of course, anything you multiply with 1 will give you that particular thing. If I say 1 times y, it will still give me y. 1 times x will give me x. 1 times the y dx will give me what? The y dx. So now I can say that the v dy now, sorry, it is the v dx. It is the v dx, not the v dy. It is the v dx. The v dx, because it is actually the v dx we are calculating. So the v dx will be what? It will be the y dx here. To be the y dx. Okay? To be the y dx, because it is this the v dx we are calculating. So the v dx, it will give us the y dx. Then I will substitute all the givens. If I substitute them inside, I will have this. Yes, this is what I will have. Because this from here to here, is the what? Is v. You can see it now. V. You can see it. Then the u dx, you can see it from the u dx. That is v times the u dx. And the u dx is minus 1. You can see the minus 1 here. Minus, you can see that this minus that is there, this is it here. Okay, then I have u. What is u? This is u minus x plus 1. You can see it here, minus x plus 1. And the v dx, and that the v dx, I told you that this is the v dx. So the v dx is now what? The y dx. So that is how we arrive at the y dx here. See it. That's how we arrive at the y dx here. And v square, so you can see it here, that is y minus 3 all brackets squared. So you can also see it here. So you can see there. Okay, so that's for that. So recall that the condition given before us is x equals to 3, y equals to what? 2. So if I substitute x equals to 3 into this formula, so if I substitute x into where there's x and y into where there's y, what will I have? Then this dy dx too, I need to substitute, I need to replace it. When we solved the y dx earlier, the first one we solved, what was our answer for the y dx? Our answer was what? 2. So that is how you can see 2 here. So that is, we have replaced this y dx with what? This is y dx that is here. We have already replaced it with what? 2. By the time we calculated our dy dx and we substitute the value of our x and y, we arrived, the answer we got initial was what? Was 2. So we have replaced it with 2. So if I then replace x, y, If I replace them with their boundary condition, I mean with their condition given here, so this is what we have as the final answer for the square y over the x square. So therefore, at point 3 comma 2, the y dx is equals to 2 and the square y dx is equals to 5. Please stay tuned for more videos. Consider to share the videos, consider to like the video, consider to subscribe and turn on the notification button anytime, so anytime I upload new videos, so that you can get notified. And um drop your own view in the comments. If you have any questions, drop it in the comments. See you in my next video.